Okay, welcome back. The live is starting again. So now we have a 1 hour session on KM3NeT data analysis by Jutta Schneider.
Okay, and we'll dive right in. And it's not actually going to be only me, because Tom, who just gave the last lecture, is also part of KM3NeT and one of, or I think at least one of the most key developers at the moment. So we're doing this together, but I'm gonna start. Just to give you a short introduction to neutrino data, or how you can handle neutrino data in this open science context. Why neutrinos? We have a collaboration that is just starting, a detector that is just in the building phase, and of course the typical history, as all the sciences, of having a lot of legacy way to work and a lot of legacy code that we are dealing with, and that we are now trying to move towards an open science context. So this is also a bit about the way we are trying to make to a fair environment in KM3NeT, so as an example for a larger collaboration. So how am I going to do this? So in the beginning, just for you to understand what kind of physics we're talking about, a very short introduction into our ultra-high energy neutrino environment and the detectors we're using. And then using an example by Antares, which is basically the older but smaller sister of KM3NeT, we'll just show how we were progressing from, let's say, the old style, where the CSV table that you could download somewhere or get from your colleague by a nice request is progressing nicely towards an interoperable environment. And then last but not least, Tom is going to give a short introduction in a small hands-on analysis to a possible analysis workflow with a full data set. So the physics we are talking about is ultra-high energy neutrinos. And basically in KM3NeT, we have the possibility, as well as in other experiments of that scale, to target different areas of physics, actually. So the primary goal is that we are looking for astrophysical sources of neutrinos that could be galactic or cosmic sources, where these neutrinos are produced in accelerator regions, and where they are a unique messenger for this kind of physics. And where we are dealing with very low count rates. So there have been the first discoveries of this type of neutrinos, but generally we are looking for needles in a haystack. But secondly, you can also do a lot of particle physics actually with this kind of detectors, because the atmosphere gives us a great source of neutrinos for free, which you can use to do oscillation physics. These oscillation patterns can be analyzed to enhance our knowledge about neutrinos in quite multiple ways. So we basically have a dual use detector, but that also means that we are standing with 1 feet in 2 different kinds of physics environments with different standards, with different ways to do things. So how are we actually dealing with these neutrinos, and how does the data look like that we are getting out of our detectors? So the main principle is basically that we are looking for the secondary particles that are produced by neutrino interactions, which are passing through a dense medium, which is here water, produce Cherenkov radiation, and we detect these Cherenkov radiation in photomultipliers. So our data looks like a long array of photons, basically, that is distributed somewhere in the sea, from which we have to reconstruct the direction and energy of the original particles. For these ends, we have two arrays that are currently under construction. One is ORCA, which is dedicated to neutrino oscillations. Because the energy of these neutrinos is generally a bit lower, it's also a bit denser kind of detector, so the PMTs are just closer to each other. And the second is ARCA, which is dedicated to the high energy end of astrophysics, which is much wider, has a much wider spacing. So the general, I hope that plot is going to come. So the general idea is that we have, no, you're going to have to see that way. So the general idea is that we have this dense medium, natural medium, which could be water or, for example, ice. So Ice Cube is a similar experiment that is operated on the South Pole that uses ice for the same purpose. And we need a really big volume because of the low count rates that we are looking for. And last but not least, we have the problem that we have to tell our neutrino products from interactions that are produced in the atmosphere. There are these kind of particles from the atmosphere that we would like to detect, which would be neutrinos, because we can do our oscillation studies with them. But there are also this kind of particles that we don't like to detect that much, which are actually muons, that are produced in the atmosphere but have no relation to our neutrinos. So these we have to filter out as a strong background. So we are moving deep into our medium, deep into the sea or the ice to get rid of this background. And most of all, we use the Earth as a shield to distinguish between a muon that came from a neutrino interaction and a muon that came actually just from the atmosphere. So all these neutrinos coming from below are what we're looking for. So as you see, we have an environment that is has a large number of factors that can influence our data, and where we have to do a very dedicated study to actually find these few neutrinos that we are interested in. And to actually get this, we need dedicated simulations for the whole process. So our data more or less becomes meaningless, not meaningless completely, but to a large extent meaningless if we can't deliver these kind of probabilities that come with the data set for the actual measurements. So these kind of searches that we are then doing are, for example, to see if there are clusters of neutrinos that we filter from our data that come from a certain direction, which would be a point source analysis. So we were looking for dedicated objects that produce these neutrinos. Or we have a list of candidates where we see if there are coincident neutrinos. And as an example analysis that we are now using to get to this move to fair data done is here the Antares point source analysis. So with Antares, as you see, we have a data set that spans 10 years of collecting neutrinos. And on the right-hand side, you can see how this analysis basically is presented. So we have a paper. We have these 10 years of neutrinos, and we have a website where you can find all the information. And so this web page basically has the data to download and these plots here to use for you. You can request access to the event list, and what you end up with is this. So we have a CSV table where we have nicely labeled columns with here basically the standard information that we have for each neutrino. So we have a direction, a declination, and right ascension. We have the number of hits. So number of hits here basically means it's an energy estimate. So it means how many photomultipliers have measured photons. The more photons we measure, the more secondary particles, the higher the energy of the original particle. We have a kind of angular error estimate, which is called beta, and the Julian date here. So what can we do with this? Well, of course, using pandas or your tool of choice, you can basically here use the first example notebook, but I think you can probably also do this by hand by now. So we can just read this CSV table and start to do any kind of cuts, for example, you want to do on this. But of course, we already hit the question, what is declination and what is right ascension? Which reference frame are we talking about when we talk about declination and right ascension? So to actually make this usable here, you need to understand, first of all, which coordinate system it is in, and you have to transform it. And then basically you probably start modifying your data and give it out in this kind of right ascension and declination in the format that you want to have it in. So that can be done, but it requires quite a lot of steps. So to move on from this, the next step, or the first step we took, is we discovered the virtual observatory. I think we already had, some mentions of those, and I'm not going to give a full-scale introduction into the virtual observatory, but I just want to mention quickly what the advantages of, first of all, this kind of standardization that comes from the IVOA offers, and secondly, also give you a short insight into this very little part of what I understand on how to use VO tools. So the virtual observatory basically is a standard setting organization or a collaboration of different institutions which have sat down to standardize their interfaces. So the IVOA defines basically everything that happens between the data provider, so any kind of astronomical observatory can become a data provider, or institutes and so on, and they provide their data, could be images, could be tables, or other kinds of objects, and they define basically all the access protocols. On the one hand, the access protocols, and on the other hand, they basically provide a big registry. So as we heard of registries like Zenodo, for example, where you can upload a lot of different styles and data, and where it's not that that strongly systematized. In the virtual observatory, there is basically a very dedicated kind of registry and a very well annotated kind of registry. So through this access layer, it makes it much easier for you to find your data sets and also to understand how you can interact with these data sets. And so what we did is basically we became one of these data providers. And there's thankfully also you don't have to start from scratch and program all your different interfaces yourself. No, of course there are packages that can do that for you. Here, for example, the perhaps a bit anachronistically looking but very useful DAX software. So this is basically a software package which lets you define with exactly the same data set that we had here, lets you define what is actually in my table, how do I describe all the different columns that I have, who provides the data, what kind of license is there on the data. So all these kind of little things that you never think about if you want to use data, but that are somehow important in the end, because if somebody didn't actually give you permission, for example, to use the data officially, you might run into trouble later when you're using it for your research. So all these little things are covered in this kind of repository information that you give here. And so what we had before as the CSV table becomes basically this kind of described annotated table with a lot of identifiers which by first look don't mean much to you, like for example here like a UCD, so a unique content identifier, but which tells the system basically, and also you, okay, what we have here is a right ascension, and it's in a certain format. Of course, if the software knows that, it's much easier to transform from one format, for example, into the other. You basically provide the data through this interface. Then this virtual observatory endpoint basically becomes known to the registry by just registering it. And then it makes it findable. So there are different endpoints, like, for example, the TAP protocol, which is for tableized data, but there are also different other access points, which then make it easy to actually I hope you're still seeing my screen, because I'm having some glitches here.
Yes, we see your screen.
Okay, great. So which then basically make it easy for a nice program like Allerton, which is a observatory software, to find your data and to also display it. So this is one of the VO software products that you can use. And it's apart from the fact that it's really graphically nice, it lets you also here easily interface and find data. So we see here on the left side basically the whole registry of all the different data sets that the VO can provide, and it's we have 26,000 collections actually that we can access here. And so I can see if I can find my Antares data in here. And what we see, first of all, Antares has published with a different institute some of the data sets before, but we can also find our new and not yet well annotated data set. And I can see, I select here a certain area of the sky, and I can just load my neutrino data set and can display this neutrino data. So from the CSV table, we have come to something that we can access in this kind of software. We can cross-correlate and so on in some other environment. And of course, because we are heavily focusing on Python here, there's also a Python client for this, which is PyVO. So to use it in a notebook, have a look at PyVO, and I'm just gonna mention this here. And also there are some nice tutorials. So PyVO comes with a lot of description, what you can use. And basically what it does, it gives you an interface to the registry. So as you see here, you can import PyVO and then, for example, call this TAP service. So TAP service was the table data. We have different kinds of data services like images, spectral access, different kind of search algorithms like simple current search, which basically gives you all the data, all the information of objects in a to a certain direction in the sky. And we can just call the service using PyVO, call this TAP service, and then use an SQL-like query language, ADQL, to search the table that we are getting back. So the TAP service gives us a table, and we can search the table with this query language, get back results, and so on, and then do whichever data manipulation you would like to do in the Python environment. So for our Antares neutrino example, we can just do this now from our own server. So we became here the provider vo.km3NeT.de, and we query the DAX server. So we just query here the whole table. So we select star from this table name. The table name we can find on the, for example, on the information on the KM3NeT VO server webpage. And we can just read from this and, for example, now here, use it in a very long way, written in a very long way, to plot the number of hits. To just plot one of the columns or select certain events from this event list. And of course, the big plus is we can't just do this for our own data, but it's easy to access different sources also. Here, for example, we combine an Antares dataset and an IceCube dataset and see if we find some neutrinos that come from the same direction in the sky. Here, in a very long way, by basically doing this, the typical way to see if I actually find something from the same direction. But as I said before, there are also a lot of search protocols, for example, which are implemented in the virtual observatory, which you can then use to do very specific analysis. So, so this was the very, very short introduction to the virtual observatory interface. But then we have the question or the problem from before that we, if you remember this page here, we have a data set, but as I said, we cannot really interpret this data set well. We do not understand how our probability functions are, our instrument response and so on for the time that we have taken the data, and what actually our expectation for the neutrino flux is. So if we do not know how many neutrinos we should have measured from a certain direction, the result that we have measured 0 or 1 or 2 neutrinos is quite meaningless. So what we need is actually additional information. So as effective areas or detector acceptance, as you can see in the plots down here. So every publication usually has this additional information. The problem that we are hitting is the virtual observatory is built for something like comparing your radio image with your optical image, for example. So comparing small regions in the sky and analyzing from different sources there. With neutrinos, we have basically the whole sky as our observed area, or at least a large part of it, and much longer time spaces, and not really image data as such, but this table data. So interpreting this kind of data needs the additional information that we see here. And in the virtual observatory, so far there are not really the ideal protocols for this. That's the one hand thing. And secondly, remember, we're doing neutrino oscillation research as well. So we basically also want to talk to particle physicists who do not know or do not use the virtual observatory. So we need to find good ways to offer this data and interfaces also to this community. And this is where, of course, we come down to doing our own custom-made interfaces, which in the end are supposed to end up, of course, in a common infrastructure with other experiments. So welcome to the ESCAPE school. This is also where we hope that ESCAPE is heading. So the question is, what do we do about all the rest of the data that we want to offer? And what we have in place now as a really small demo and just under construction is basically that we offer them through our own server. So you can also directly download them from the server. And we have a small Python package, a client, that allows you to access this kind of data. So this small package called OpenKM3 that interfaces with the data center API, provides functions to download and to interpret the data products. And as I said, it goes a bit beyond what the virtual observatory offers, because the physics is different and the communities are different, but it also integrates with PyVO. So what we how you can use this is basically by you just need it once, but once. So you can basically import here, and because it's not installed in the standard school environment, and it's anyway not yet registered with PyPy, so you can only directly install it from our Git repository. Here a small command how you can actually install it when you run this. So when you run this Jupyter Notebook, you just run the cell once, and it installs your installs the OpenKM3 package in your environment. And then what is the main feature of the package is you have a KM3 store. So you call the store, and the store basically loads the information which data is available from the server, and you can get a current list of all the available data sets. Remember, it's just a demo data at the moment, so we don't have that many, but we have our Antares analysis that we were just talking about available here in the data store. So what you can get then for the different event data that you have here, we basically also have, by the way, acoustic data. So the detector cannot only see neutrinos, our detector can also hear neutrinos. Which is interesting for sea scientists as well, because they, if you put microphones in the deep sea, you cannot only try to listen for clicks from high energy neutrinos, but also, of course, from songs from whales or other kind of deep sea animals. So we also actually offer information here that is interesting for biologists in the end. So you can access this data and get more information by just using the identifiers. So here we get a list of all the available connected data entries. And as you can see, we find here the event list that we were just looking at, so our CSV table again. But you can, we also see here a publication, so it's just a pointer to the publication that's related, and these basically some of these plots that we had before. So we have the effective area, the muon estimate, so background estimate function, and the detector acceptance here now as accessible data sets. And as you can see, for example, here we can just load one of these data sets and can then use this further in the analysis. So as I said, this integrates well with the PyVO environment. So if I use something that is actually something that is taken from our virtual observatory server, so our Antares dataset from before that we put on the virtual observatory server is now available here also through the KM3 store. So we have here this VO dataset, and we have additional functions that come with it, OpenKM3 package. So for example, of course, this is just a list, but it gives you basically the table of with the information on the dataset, how it is displayed on the VO server. And then it interfaces, as I said, to the PyVO package. So I can now use this data set also with functions that I know already from PyVO. So here, for example, I get the tab service for this data set. And I can use, as you see here, the same call as before to search for specific entries here, for example, with the number hits larger than 150, and produce, for example, it's now here a pandas table out of it. Same is true for this for the simple cone search. So the simple cone search is, as I said before, basically a protocol where you can search around a certain declination and right ascension with a certain opening angle, which makes it, of course, much faster than our count method that we had before between the two IceCube and Antares data sets to find objects or entries that are close to each other. And of course, you can still access the full table. So that's this. And of course, last but not least, as I said, what we can do now is actually access this additional data. So if we use these high-level data sets, basically what we have here are projections from our simulations. So for the whole runtime of the detector, we are basically simulating the number of the expected events for neutrinos, of course, with a much higher accuracy than from our background, but so we generate really large simulated data sets. We cannot offer this to everybody, so nobody wants to download gigabytes or terabytes of simulated data to run through this to produce plots. So what we are offering here basically is really the boiled down and reduced version of approximately the information that you need to analyze the data in the context of an analysis of your specific analysis. Here again, so now from the store, I don't get the VO table, but I get, for example, this acceptance and get my description, which are actually the different axes. Do they have a unit? Even also here, do they have even a symbol if I want to autoplot that? I can also, because it's a lookup table, I can, for example, look for a certain given X value and Y value. I can get now, for example, the acceptance towards a certain declination in a spectral index, and I can get this as a function. I call it here with the X value 100. Well, I can see here that my range for the X value is -90 to 90, so that might not be a good idea to call 100 here. And let's see if something else works. No, that still doesn't work. Yes, because the Y value is 10, but a spectral index should be somewhere between 1.5 and 3. So let's do 2. And we can get an acceptance for a given declination and spectral index. So spectral index here for our neutrino flux. And the same, so the same we can have here for a background, for example, for a background function, and get for a certain declination now an estimated number of backgrounds for the whole data set. Okay, so this is basically where we are right now, and of course where we hope to connect to also other experiments and extend all these capabilities depending on the different ways we want to use the data. But let me, before I hand over to Tom, just quickly say, of course, just offering the data is not everything. So it's not enough. We have to basically always think about open science in a wider context. So you have to understand what the data does that we are offering to you. You have to be able to use our software. You have to be able to find our data and really download it easily and access it. So what we're trying to build is basically a whole open science system in the collaboration. So that starts with, of course, offering the data and offering also quality data, which is, as everybody knows, making high quality data is basically the core challenge of science. Well, one of them at least. So we are trying to produce this, but we of course also have to offer this, make it accessible, and also add education and knowledge to that. So we have an education portal where you can find a bit longer introduction courses to our data usage, which is, as I said, just at the beginning. So this will grow in time. We have an open science portal which describes also the concepts that lie behind the different data that we are offering. And also we offer, like all other big collaborations, of course, our software as open and as easily accessible as possible. Also providing Docker containers and so on. Before I hand over to Tom, who will tell you a bit more in depth and show you a bit more in depth an example analysis on basically the real KM3NeT data, because so far we just looked at Antares. I don't know if there are any questions we should answer in the meantime. I don't think so.
I don't see any urgent question. I think you can go on.
Okay, then I think Tom?
Yes, can you, okay. So let's see, I will share my screen. We will quickly go through this example notebook. Of course, there are many things which we could cover regarding KM3NeT. There's a lot of data, and we will make a lot of them, many different data. I mean, will be made openly accessible. So it's of course hard to pick something interesting, but at least there's this package called KM3NeT test data, which you can install. This contains small sample files of different things like detector calibration and Monte Carlo simulation. So everything is just dummy data, don't make any sense of it. Just shows our structures, the root files which we use, the HDF5 files which we use, stuff from Genie, Corsica, other software which we use. So yeah, all the stuff is there. If you install this pip package, you will get access to this data path function, which you can use to get the path of a test file. So this is what I will use here to grab some sample file. So this is a basic analysis example. It's not really in depth, like Jutta said. It's just to show how our data looks like. So maybe it's a better phrase like this. Okay, so as usual, I import Matplotlib and Pandas, NumPy, also KM3pipe, which is one of our main Python frameworks to do the pipeline stuff, and there are some helper functions to KM3NeT related stuff. We will only use Zenit and Azimuth here, which is of course always a bit confusing from experiment to experiment. These are defined differently. And then Seaborn for some beautiful statistical plots, and yeah, as I mentioned, the KM3NeT test data path. KM3pipe comes with its own matplotlib style, so if you execute this, then the plots will look the same, no matter what kind of configuration you used before. I've used this just for conciseness. You can skip it completely. So as I mentioned before, we use root and HDF5 files. These are our main data formats for low-level data and also high-level data. But there is this H5 extract tool in KM3pipe, which you can use to convert root data. So whenever you are facing some kind of a root file coming from KM3NeT, you can use KM3pipe to convert it to HDF5. It uses uproot, which you have learned on Monday from Eduardo Rodriguez. It's a Python pure library, and also KM3pipe only relies on Python tools. So this uproot is used to read the root file contents. So you don't have to install this heavy root package to open our files just to read some data. Okay, so this is the command to extract it, just in case for future reference also. So this notebook is pre-prepared, so I don't have to type anything now, just hit Shift Enter. Sorry for that, but of course you will find this notebook and the updated version afterwards. We just go quickly through them just to get you look and feel how a basic analysis would look like with some with our sample data. So this is the file which we're looking at. It's in the HDF5 folder and called basic analysis sample of this, which is accessible with this data path from the KM3NeT test data package. So this is the path on my computer. This is what you get back when you call this function. It's in this miniforge, blah, 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 etc., etc. You can use this pt dump function, which is coming from, oops, sorry for toggling it all the time. This is coming from PyTables. This is a command line tool. So if you go to your terminal or you type an exclamation mark and then the command followed by this path, then you can execute something in the shell. The result will be returned here. I like this function because it quickly gives you a summary of what's inside this HDF5 file. As you can see, there is an event info. This is where we always store the information for each event. So each row is one event, and in these events, in these rows, we have done specific values or parameters describing each event. Then there are Monte Carlo tracks. There are 25,000. So there are multiple tracks for each event. I will come to that later, how these are grouped. And there's a reconstruction folder. And in this example file, there is only one reconstruction method, which is called the Gandalf, the J Gandalf reconstruction is how we call it. And it reconstructed one track for each event. That's why you see the matching numbers here. So in Monte Carlo tracks, you have the incoming neutrino and a lot of secondaries. And here, in this case, the reconstruction will spit out one reconstructed track for each event. So let's have a look at the event info. As you may have seen in the pandas lecture, we can use pandas for this. So pandas read HDF5 is the function to read something from this HDF5 file. And we will have a look at this table, which is stored under event info. If I read that in and print ahead, you can see that this is how the event info looks like. So as I said, each row is one event. The first event, the detector ID in this case is -1. This just means that it's just a generic Monte Carlo simulation and nothing serious. There are parameters like Monte Carlo time, then trigger mask, etc., and weights. If you want to reweight the flux, the neutrino flux, etc. But this is not part of this presentation right now. Yeah, and this is of course a pandas data frame. So you have the usual things like d-types, and you can access each column by either the property syntax, so writing event info dot and then the name of the column, or the dictionary syntax. Let me snooze my notifications. Like this. This is now the dictionary syntax, so the same column accessed in a different way. So yeah, let's read in our Monte Carlo tracks, and I store it in the variable tracks. So I use again pandas, read HDF5, file path with this Monte Carlo tracks. And it has now similar structure as this event ID, but we have multiple columns per event. So here you can see the first 10 entries, and there is this event ID, or in newer files, you will find it group ID, which we use to identify which track belongs to which event. In this case, the first 5 tracks belong to the first event, and the next 5 or even more belong to the second event. So if you want to group them and correlate them with other data, you have to use this column as your index. Here I can get access to the primaries. This is something KM3NeT specific. So in the Monte Carlo tracks, we always store the neutrinos as the first entry in the track list. So this is the first neutrino. You can also recognize this -14 maybe. It's a PDG ID. You can use the particles package for Python to convert the PDG ID to readable names. But if you're working with neutrino telescopes, you recognize this 14, etc. So this is the incoming neutrino for the first event, the incoming neutrino for the second event with the ID 1, etc., etc. So this group by operation, which we also covered in the pandas section, groups all the Monte Carlo tracks by event ID and then picks the first row. And we store them here in the primaries variable. So this is how our primaries now look like. You can see that here, that's a neutrino from the first event, from the second event, etc., etc. And the index is now the event ID. So let's make some fancy plots. We can, for example, look at the reconstructed energies as a histogram with 100 bins in a logarithmic scale. This is looking like this. So again, we're using here just the column energy and matplotlib for plotting, which we also covered. So this should be now quite easy to do for you. We can also look at the Bjorken Y distribution. So this is our Birkenwald distribution of the, so this is coming from the event properties. And now if we want to have a look at the Zenit distribution, then we have to use this tiny little helper function from KM3 This is just to make sure that we are using the same Zenit definition as that you are using the same Zenit definition as we do. And I used here a little trick. So if I get this primaries, I want to have the direction x, y, and z. So there you can use the filter function and then the regex, which is regular expression. So this basically looks for columns which are matching this regular expression. If you look at the primaries quickly, head 1, you can see that we have these columns like dir x, dir y, and dir z. So from this we can calculate the Zenit. And if we apply this filter, this will only show the corresponding columns. So if I, for example, replace direction with position or so, it will only show the positions. Okay, so this will pass to this function all the positions as a vector. And yeah, we just store them in the primaries again, so that we have the Zenits for later access. And then we plot the cosine of the Zenits in a histogram, which will look like this. Okay, maybe you're interested in the starting position of the primaries, so of these neutrinos, just to see how they are generated in the volume. So there we can do a 2D plane. This is just a 2D histogram of the Z and Y positions of all the primaries. And there is also this nice way of using Seaborn to do this. I like these hex histograms, where you can also have these projections on the Y and X plane as histograms to analyze. Okay, so let's have a look at some 3D distributions, just in case you want to do something in 3D. This is how our events are. So these are the starting positions of the neutrinos. Here I'm using the mplot 3D. This is a fairly old way of doing things. There are better ways nowadays, which are a bit more shorter, etc. But yeah, it works, of course. Okay, so let's have a look at how to correlate this stuff. So as I mentioned, we have this Gandalf reconstruction here. So in this Rico folder in the group in the HDF5 file, there is this Gandalf dataset. And if we read this in, this contains now one track for each event which was reconstructed. So there is this reconstructed direction and reconstructed energies and and a few other parameters which we can or also use to cut the data, so define some quality criteria, etc. These are the columns which are described in our publications when we release these open data. And for now, we do a quick Zenit plot with the same trick. We filter all the directions and pass them to the Zenit function of KM3 and this is the reconstructed Zenit difference. So what I did here is I took the Zenits and I subtracted the primaries Zenits, so the neutrinos. So this is basically now a comparison of how good my reconstruction is without any cuts. So here you expect, of course, a spike. So the events in the middle of this histogram are filling this because they are quite accurately reconstructed. Of course, 0 means no error at all. Yeah. So Gandalf has a parameter called lambda. We can define a cut on it so depending on the needs or on your quality cuts. This is just a basic example of how to do some kind of cuts. So I'm defining this mask where I said that I'm interested in the reconstructions where the lambda is less than 0.2. And I can redo the same plot, and you can see that if you compare this plot to the one above, it's a bit more narrow, fairly more narrow actually. But let's compare them a little bit better. So here I'm iterating over different values of lambda, and there you can see that you can set your lambda. You can make your cuts better and better, so the actual reconstruction will be better. But of course, you also lose a lot of events. And finally, there is a small example. This was provided by Moritz to fit some angular resolutions. It's a bit long, and I think I only have just a few minutes left, so let's go not over it in too details. But here I'm using this using these fit functions to do some fitting and multiple plots. So if you see the end result, you can see here how we use different methods to fit stuff, and you can compare them. And yeah, we included this example because this is done a lot, and there are just a few different methods to do things, but there are of course better introductions to these things. And last but not least, there is this small example with the median absolute deviation, which you can also calculate like this. Okay, we just leave it there, I guess, and then we almost did the full hour. So sorry that it's a bit short or not so in-depth, but yeah, we don't have too much time to go into detail. And if I start, then we will never end. Okay, so many thanks for your time. I scroll back, and you find this whole notebook, as I said, updated after the talk. The current version is also there. I cleaned it a bit up, and of course I will upload this one, so it's newly executed. Thanks.
Thank you, Tamas and Jutta, for that intro to KM3NeT and its data. I don't see any question in the chat, so I will ask myself. What is the volume of data that will be produced by KM3NeT?
You mean now for publication or in general?
I mean the data that will be publicly available.
Okay, yeah, that's actually a good question. So we will make, well, maybe Jutta can help me to answer these questions a bit better, because she knows the numbers, I think, better in case of what are the restrictions. But I think that we agreed to release basically everything up to 2 years. But of course, it's not so easy to release like a petabyte or so per year of data. So there will be multiple levels of data which we release. And so we have the highest level data, which is the reconstructed stuff. Then we have a lower level data, which contains maybe multiple reconstructions, so that you have multiple reconstructions for each event. And then it goes, of course, down further, like hit level data, where you can visualize events in the detector, or even things like environmental data, what Jutta showed us, where we can have sea currents or sounds of the ocean to study, to do studies on other fields. So yeah, it's complicated, different levels, and it depends on the needs. But whenever someone needs something, they can always contact us, and we will find a way to provide the data. So this is the general approach. Like, we will not publicly make everything online and then just download, let the people download petabytes or whatever, but figure out a way to access those. Maybe Peter can extend on that, or
I think it's a question of the interface, because if you want to have big volumes of data, and as I just said, the crux is basically that we have to do that you have to be able to use the simulations to really do a fine-grained analysis, and this is something you can't handle anymore through an easy API downloading from one server, but you need a computing infrastructure, HPC infrastructure behind that probably to do it. And of course, that's what we are working towards in ESCAPE, so that if you're certified with a certain provider perhaps, or with an institute, or through your institute, that you can also use computing resources to actually use full data sets. Then when we're talking really about large data sets for several years of KM3NeT data, because you can't do it anymore through usually just downloading your stuff. But this also this high level data that was just shown here. So of course it's 10 years of Antares data, but what remains in the end of this level 4 data, so the reduced data, is small and will still of course be provided in a way that you can do it without HPC access.
I see. Thanks. And concerning the biology data, do you have like partnerships to share this data, or is it just open?
So at the moment, we're just offering, let's say, snippets of data, and but we have collaborators actually from C-Science in our collaboration. So not all our collaborating institutes and scientists are astrophysicists or even physicists. So they are accessing the data already, and but again, here it's a very community-specific way of handling data. And if we want to offer it on a wider scale, we just have to figure out how to do it, and we're just developing.
Sure, but so you have collaborators in the collaboration in KM3NeT, people from C-Science.
Yeah.
Ah, great, thanks. Okay, well, that's it for me. Thank you very much again for the presentation. We will do a 5-minute break just so you can prepare for the next session. That will be an introduction to gravitational waves data analysis. So we resume in 5 minutes, and I will send the instruction in the announcement channel. See you in 5.